you always want to be putting your vectors into columns, not rows. I still see a lot of people doing that, even on this last exam. The vectors need to go into the columns of this matrix. That's the best way to do it. Okay, so finding a basis for V. Of course, you need to know the standard vector spaces, polynomials, matrices, Rn, and their dimensions. You need to know those things for sure. There were a few people on the midterm the other day that told me that the dimension of M3 of R was either 3 or 6. No, it's 9, right? It's n squared. So make sure you know the dimensions of the vector spaces that we work with on a daily basis. Definitely. Okay, and then, of course, there's a great way to get a bunch of examples is to take any matrix, M by N matrix, say A, and you can talk about its null space, row space, and column space. So, so you could find bases for null space, row space, and column space. All of those concepts are kind of important. Null space, row space, and column space. In all cases, you need to row reduce the matrix A, find your pivots, and the number of pivots would be the rank, and that's the dimension of the row space and the column space. The number of non-pivots would be your nullity, and that's the dimension of the null space. And remember that the rank plus the nullity, this is an important formula here, the rank plus the nullity always adds up to n. N is the number of columns, right? N is the number of columns. This is a great formula. We later generalized that when we learned about kernel and range of a linear transformation. Remember that? The dimension of the kernel plus the dimension of the range equals the dimension of V when you have a linear transformation from V to W. So this was the early version of the formula, which we later expanded to more general situations. Okay, so we have that, the rank nullity theorem, null space, row space, column space. And then kind of at the end of chapter 4 is a good time to take inventory of the invertible matrix theorem. I don't want to write the whole thing out again, I just wanted to put that on the board to remind you. It is in the back cover of the book, this long list of statements about invertible matrices. It would be good for you to review that kind of from a theoretical point of view, but also just to, again, make connections between different things we've talked about all semester long. They're all kind of tied together in that. Okay, so that's the invertible matrix theorem. And then finally, the last little bit of chapter 4 is the inner product spaces. So inner products. This is where we had notions of norms and angles and so on, some of the geometric insights that we can put onto a vector space. So you're going to want to know the axioms of an inner product. The most important one is the first one. The first axiom just tells you that the inner product of x with itself has to be at least 0. It has to be a positive number. Or it could be 0, but only if x is 0. So equals 0 only if x is equal to 0.